Could you stand on the surface of another world and survive? Imagine this. You step out of a pressurized airlock and your boots sink into rust-colored dust that has not been touched by a single living organism in over 4 billion years. The horizon stretches in a sickly ochre arc. The sky above you is not blue but a washed-out butterscotch haze, and the sun hangs small and pale, casting about 43% of the light you are accustomed to back home. There is no wind you can hear because the atmosphere is so thin that even a gale blowing at 220 miles per hour would feel like a gentle breeze against your suit. The silence is not peaceful. It is the silence of a world that never learned to breathe. Your own respiration echoes inside your helmet, and every exhalation fogs the visor for a fraction of a second before the environmental system scrubs the moisture away. This is Mars. This is the place where some of the most ambitious engineers and visionaries of our era believe humanity should build its second home. But can we really live here? Can we raise children here? Can we sustain a civilization here? And perhaps the most uncomfortable question of all, should we abandon the only planet that has ever kept us alive in order to gamble everything on a frozen, irradiated desert roughly 140 million miles from everyone we have ever known? Mars colonization is not a romantic daydream. It is not a poster on a teenager's bedroom wall or a catchy tagline from a billionaire's press conference. It is a brutally complex intersection of physics, evolutionary biology, energy engineering, psychology, political economics, and moral philosophy. Every single system that keeps you alive on Earth, the air pressure that holds your blood together, the magnetic field that blocks lethal radiation, the gravitational pull that shaped every bone and muscle fiber in your body, the liquid water cycle that sustains every ecosystem on the surface, is either absent or critically degraded on Mars. Homo sapiens spent roughly 3.8 billion years of evolutionary history optimizing for the conditions of one specific planet. We did not evolve for Mars. We evolved for Earth. And the distance between those two statements contains the entire drama of what it would actually take to put a permanent human settlement on the fourth rock from the sun. So let us dissect this. Not with hope, not with cynicism, but with numbers, data, and an honest reckoning of what science currently tells us about the possibility and the price of becoming a multiplanetary species. The environmental conditions on Mars are not merely difficult. They are actively hostile to every biological process that sustains human life. The average atmospheric pressure on the Martian surface is approximately 610 pascals. To put that in perspective, standard sea-level atmospheric pressure in New York City or Los Angeles is about 101,300 pascals. Mars has 0.6% of that. The atmosphere is composed almost entirely of carbon dioxide, roughly 95.1% according to measurements taken by NASA's Curiosity rover using the sample analysis at Mars instrument, with 2.6% molecular nitrogen, 1.9% argon, and only 0.145% molecular oxygen. You cannot breathe this air. You cannot even survive in it without full pressurization. If you were to step onto the Martian surface without a pressure suit, you would lose consciousness within approximately 10 to 15 seconds. The reason is not just the lack of oxygen. At pressures below the Armstrong limit, which is about 6.3 kilopascals, the boiling point of water drops below human body temperature. Your saliva would begin to boil on your tongue. The moisture lining your lungs would vaporize. One NASA test subject who was accidentally exposed to near-vacuum conditions in a pressure chamber reported that his last conscious memory was the sensation of the water on his tongue beginning to bubble. He survived because the chamber was repressurized within seconds. On Mars, there would be no repressurization. You would be dead in under 2 minutes. The average surface temperature on Mars is negative 63 degrees Celsius, which is negative 81 degrees Fahrenheit. At night, temperatures routinely plunge to negative 100 degrees Celsius or colder, depending on latitude and season. During a Martian summer afternoon near the equator, temperatures can briefly climb to around 0 degrees Celsius. But this provides no comfort because the thin atmosphere cannot retain heat. The moment the sun dips below the horizon, temperatures crash. This is partly because the greenhouse effect on Mars is extraordinarily weak. On Earth, water vapor and carbon dioxide trap enough thermal radiation to raise the average surface temperature by approximately 33 degrees Celsius above what it would otherwise be. Mars has abundant carbon dioxide in its atmosphere, but the atmosphere itself is so thin that the total greenhouse warming amounts to only about 5 degrees Celsius. This is a critical point that undermines many popular assumptions about terraforming. Simply adding more carbon dioxide to the Martian atmosphere will not produce significant warming unless the atmospheric pressure itself is dramatically increased. And as we will see later, there is not enough accessible carbon dioxide on Mars to accomplish that. Water cannot exist as a stable liquid on the Martian surface under current conditions. The combination of low atmospheric pressure and low temperature means that water transitions directly between solid ice and gaseous vapor, a process called sublimation, without passing through a liquid phase in most surface locations. There is no rain on Mars. There are no rivers, no lakes, no oceans. There is ice, vast quantities of it, buried beneath the surface and concentrated at the polar caps. A 2025 study published in the Planetary Science Journal refined our mapping of subsurface water ice and confirmed that more than 5 million cubic kilometers of ice exist at or near the Martian surface, enough to cover the entire planet to a depth of about 35 meters if it were melted and spread evenly. Some of this ice is located at mid-latitudes in regions like Amazonas Planitia, where it lies relatively close to the surface, making it a potential target for future extraction. But extracting, melting, purifying, and utilizing that ice requires enormous energy inputs. And energy is one of the scarcest commodities on Mars. Consider the seasonal dynamics. A Martian year lasts 687 Earth days, nearly twice as long as a year on our planet. The axial tilt of Mars is about 25.2 degrees, similar to Earth's 23.4 degrees, which means Mars does experience seasons. But because the year is longer, each season lasts roughly twice as long. Winters are brutally prolonged. During winter at the poles, temperatures drop low enough that carbon dioxide freezes directly out of the atmosphere and accumulates as dry ice on the polar caps. This seasonal freezing removes so much gas from the atmosphere that the global atmospheric pressure drops by as much as 25%. When the carbon dioxide sublimes back into the atmosphere during spring and summer, it generates powerful atmospheric currents that kick up dust from the surface. These dust events range from small localized phenomena called dust devils, towering columns of spinning dust that are common across the Martian landscape, to planet-encircling dust storms that can last for months and shroud the entire globe in an opaque haze. The 2018 global dust storm famously ended the mission of NASA's Opportunity rover after nearly 15 years of operation by blocking so much sunlight that the rover's solar panels could no longer generate enough power to keep its systems running. For any human settlement relying on solar energy, a global dust storm could be an existential crisis, cutting power generation to near zero for weeks or months at a time. The Martian surface itself presents chemical hazards that are not immediately obvious from photographs. The distinctive red color comes from iron oxide, essentially rust, which permeates the soil. But the more insidious threat is perchlorate. Data from the Phoenix lander and subsequent missions confirmed that Martian soil, technically called regolith, contains perchlorate salts at concentrations of roughly 0.5 to 1% by weight. Perchlorate is toxic to humans. In the human body, perchlorate interferes with the thyroid gland's ability to absorb iodine, disrupting the production of thyroid hormones that regulate metabolism, growth, and development. Chronic exposure can cause hypothyroidism, and there is evidence linking perchlorate to increased cancer risk. A 2024 review published in the journal Icarus surveyed decades of perchlorate research and confirmed that these compounds are widespread across the Martian surface, not confined to any particular region. This means that any attempt to grow food in Martian soil must first deal with perchlorate. Contamination. NASA-funded researchers have been developing genetically engineered bacteria capable of breaking down perchlorate into harmless chloride and oxygen. But this bioremediation process is still in early stages and has not been tested in actual Martian conditions. Even if the perchlorate is removed, Martian regolith lacks the organic nutrients, microbial communities, and structural properties that characterize fertile soil on Earth. Converting Martian dirt into something capable of supporting plant growth would require extensive processing, amendment with organic matter, and potentially years of microbial cultivation. The radiation environment on Mars is one of the most serious and least discussed threats to human habitation. Earth is protected by two overlapping shields. The first is the global magnetic field, generated by convection currents in the planet's liquid iron outer core, which deflects the vast majority of charged particles from the solar wind and cosmic rays. The second is the thick atmosphere, which absorbs and scatters the radiation that does make it past the magnetic field. Mars has neither of these protections in any meaningful sense. The planet lost its global magnetic field billions of years ago, likely as its smaller core cooled and solidified, shutting down the dynamo process. Some localized remnant magnetic fields exist in the southern highlands, detected by the Mars Global Surveyor spacecraft, but they are far too weak and patchy to provide planetary-scale protection. The thin atmosphere provides minimal shielding. As a result, the Martian surface is bombarded by two distinct types of dangerous radiation. The first is galactic cosmic radiation, abbreviated GCR, which consists of high-energy particles originating from supernova explosions, active galactic nuclei, and other violent astrophysical processes. About 85% of GCR particles are high-energy protons. Roughly 14% are helium nuclei, also called alpha particles, and the remainder includes heavier nuclei and high-energy electrons. These particles travel at 70 to 90% of the speed of light and possess enough energy to penetrate several inches of solid aluminum. When they strike a material, they cause ionization, stripping electrons from atoms and breaking molecular bonds. In human tissue, this ionization damages DNA, proteins, and cell membranes. The second type is solar energetic particles, abbreviated SP, which are bursts of radiation released during solar flares and coronal mass ejections. Unlike the steady background of GCR, SEP events are sporadic and can deliver massive doses in a matter of hours. The Radiation Assessment Detector aboard NASA's Curiosity rover provided the first direct measurements of surface radiation on Mars from August 2012 to June 2013. The data showed an average GCR dose equivalent rate of 0.67 millisieverts per day. Over a full year, that translates to roughly 244 millisieverts, which aligns with other estimates placing the annual surface dose at 240 to 300 millisieverts. For comparison, the average annual radiation dose for a person living in the United States is about 3.1 millisieverts, mostly from natural background sources and medical procedures. A Mars resident would receive roughly 40 to 50 times more radiation exposure per year than an average American. During the transit between Earth and Mars, which takes approximately 7 to 9 months with current propulsion technology, the radiation environment is even worse because there is no planetary surface or atmosphere providing any shielding at all. Transit measurements from the same Curiosity mission showed a dose rate of approximately 1.8 millisieverts per day. A complete Mars mission, including roughly 6 months of travel in each direction and a 500-day surface stay, would result in a total estimated dose of approximately 1 sievert. According to NASA's models, a dose of 1 sievert increases the lifetime risk of fatal cancer by approximately 5%. This is already at or near the career exposure limits that NASA has established for its astronauts. And this estimate assumes no major solar particle events during the mission. A 2012 solar storm, one of the most powerful observed in recent years, would have delivered a potentially lethal dose to unshielded astronauts on the Martian surface within hours had it been directed at Mars. The biological damage from radiation is not limited to cancer. GCR particles, particularly the heavy ions known as Hz particles, high atomic number and high energy, are especially destructive to the central nervous system. Animal studies conducted at Brookhaven National Laboratory and other facilities have shown that exposure to simulated space radiation causes persistent neuroinflammation, reduced neurogenesis, and measurable cognitive deficits including impaired learning, memory, and decision-making. A 2016 study published in Scientific Reports by researchers at the University of California, Irvine, exposed mice to low-dose radiation at levels comparable to what astronauts would experience on a Mars mission, and found that the animals exhibited significant anxiety-like behaviors and cognitive impairment that persisted for at least 6 months. The implications for a crew making life-and-death decisions on a distant planet are sobering. Radiation also suppresses immune function. Research on International Space Station crew members has shown that space environments, including radiation exposure, stress, and altered gravity, lead to reactivation of latent viruses, reduced T-cell function, and impaired wound healing. On Mars, where medical resources would be severely limited and evacuation is impossible, a compromised immune system could turn a minor infection into a fatal emergency. Shielding against radiation on Mars is technically possible, but extremely resource-intensive. The most effective shielding materials are those rich in hydrogen, such as water and polyethylene. Because hydrogen nuclei are approximately the same mass as incoming protons, and thus very efficient at absorbing their kinetic energy. Aluminum and steel, while structurally useful, are less effective per unit mass, and have the additional disadvantage of producing secondary radiation when struck by high-energy particles. When a GCR particle slams into a metal atom, it can trigger a nuclear spallation reaction that generates a shower of secondary particles, including neutrons, which are themselves highly damaging to biological tissue. This means that in some scenarios, a thin metal shield can actually increase the radiation dose inside a habitat compared to having no shield at all. The most commonly discussed approach is to bury habitats under several meters of Martian regolith or ice, using the natural terrain as a radiation barrier. Calculations suggest that approximately 2 to 3 meters of compacted regolith would reduce GCR exposure to levels comparable to Earth's surface background radiation. However, constructing and maintaining underground habitats introduces its own set of challenges, including excavation in a low-gravity environment with abrasive soil, structural engineering against collapse, and the psychological burden of living permanently underground without natural light or views of the outside world. The gravitational environment on Mars is a slow-motion threat to human health that receives less attention than radiation, but may ultimately prove just as consequential. Mars surface gravity is 0.376 g, meaning that objects weigh approximately 38% of what they weigh on Earth. A person who weighs 180 pounds in Chicago would feel as though they weighed only 68 pounds on Mars. At first, this might seem like a minor inconvenience or even a novelty. But the human body is a product of billions of years of evolution under Earth's gravitational pull. And every major organ system, from the skeleton to the cardiovascular system to the vestibular apparatus in the inner ear, is calibrated for 1G. Remove that calibration, and the body begins to deteriorate in predictable ways. The most comprehensive data we have on the effects of reduced gravity come from astronauts aboard the International Space Station, where the gravitational environment is effectively 0G microgravity. Studies published in journals including Nature's NPJ Microgravity have documented that astronauts lose bone mineral density at a rate of approximately 1 to 1.5% per month during spaceflight, concentrated in weight-bearing bones such as the femur, pelvis, and lumbar spine. This loss is roughly 10 times faster than the rate of bone loss in postmenopausal women with osteoporosis on Earth. After a 6-month ISS mission, some astronauts show bone density reductions of 5 to 10% that can take years of rehabilitation to fully recover. And in some cases, recovery is incomplete. Muscle atrophy is equally dramatic. Without the constant resistance of gravity, muscles begin to waste within days of entering microgravity. Studies report up to 30% loss of peak muscle force and 15 to 20% reduction in muscle mass over 4 to 6 months. The muscles most affected are the postural muscles of the legs and back, the very muscles that keep you upright and moving. Mars' gravity is not zero, of course. It is roughly 1/3 of Earth's. And there is legitimate debate about whether this intermediate level of gravity would be sufficient to significantly slow or prevent the deterioration seen in microgravity. A 2020 study published by researchers at Harvard Medical School analyzed data from mice flown on the International Space Station in a centrifuge that simulated partial gravity levels including approximately Martian gravity. Their analysis showed that 0.33 g mitigated spaceflight-induced muscle atrophy compared to microgravity, but did not fully prevent it. Full prevention was only observed at about 0.67 g. This suggests that while Mars gravity is better than nothing, it may not be enough to maintain musculoskeletal health over the long term without aggressive countermeasures, including multiple hours of resistance exercise per day, pharmaceutical interventions to slow bone resorption, and careful nutritional supplementation with calcium and vitamin D. The cardiovascular system faces its own challenges. In microgravity, the absence of hydrostatic pressure gradients causes body fluids to redistribute from the lower extremities toward the head and thorax. Astronauts commonly experience facial puffiness, nasal congestion, and a condition known as spaceflight-associated neuroocular syndrome, or SANS, in which increased intracranial pressure causes structural changes to the eyes, including flattening of the eyeball and swelling of the optic nerve. More than 60% of ISS crew members on long-duration missions have exhibited some degree of visual impairment associated with SANS. The heart, no longer working as hard to pump blood against gravity, begins to atrophy and lose fitness. Some astronauts experience cardiac dysrhythmias in space, and upon return to Earth, orthostatic intolerance, dizziness and fainting when standing up, is nearly universal. Whether Mars-level gravity would prevent or merely reduce these cardiovascular effects remains unknown, and there are currently no plans for any experiment that would definitively answer this question before humans actually arrive on Mars. Perhaps the most profound and least understood gravitational concern involves reproduction and child development. If humanity is to establish a permanent, self-sustaining colony on Mars, people will eventually need to have children there. The scientific literature on mammalian reproduction in reduced gravity is disturbingly sparse. Studies conducted on rodents in microgravity and simulated partial gravity have shown that while conception and early embryonic development can occur, the outcomes are frequently abnormal. Research by Ronka and colleagues published in 2003 found that rat pups born after their mothers spent portions of pregnancy in microgravity showed altered vestibular development and motor coordination. A 2009 study by Igiri demonstrated that fish eggs fertilized in microgravity developed into viable offspring, but the extrapolation from fish to mammals is enormous. No mammal has ever been conceived, gestated, and born in anything other than 1g gravity. We simply do not know whether a human pregnancy could proceed normally at 0.38 g, whether fetal bone and muscle development would be adequate, whether the cardiovascular system of a developing fetus would form correctly, or whether a child raised from birth in Martian gravity could ever safely travel to Earth. A child born and raised on Mars might develop a skeletal and muscular system adapted to 38% gravity that would be physically incapable of functioning under Earth's full gravitational load. Such a person would effectively be a permanent Martian, unable to return to the home planet of their species. The ethical implications of knowingly creating a generation of humans who can never visit Earth are staggering and have barely begun to be discussed in any serious policy forum. The question of food production on Mars exposes another layer of complexity that popular discussions tend to gloss over. Earth currently grows food across hundreds of millions of acres of fertile soil in open air under natural sunlight with abundant water and a cooperative biosphere. None of these conditions exist on Mars. As discussed, Martian regolith is toxic, nutrient-poor, and structurally unsuitable for agriculture. The leading candidates for Martian food production are closed-system hydroponic and aeroponic facilities in which plants are grown without soil, with their roots suspended in nutrient-rich water solutions or misted with nutrient-laden vapor. NASA has been conducting hydroponic experiments aboard the International Space Station through its veggie and advanced plant habitat programs since 2014, successfully growing small quantities of red romaine lettuce, Chinese cabbage, radishes, and chili peppers. These experiments demonstrate that plants can grow in microgravity, and presumably in Martian gravity, if provided with appropriate lighting, nutrients, water, and atmospheric conditions. But scaling from a small experimental chamber, growing a few heads of lettuce to a food production system capable of sustaining a colony is an engineering challenge of an entirely different magnitude. A single human requires approximately 2,000 calories per day, which translates to roughly 1.8 kilograms of dry food mass. For a crew of 6 on a 500-day surface mission, that is approximately 5,400 kilograms of food, not counting packaging and waste. For a permanent colony of 1,000 people, the annual food requirement would exceed 650 metric tons. Growing this quantity of food hydroponically would require enormous volumes of pressurized, temperature-controlled, artificially illuminated greenhouse space. Light is a critical constraint because Mars receives only about 43% of the solar energy per unit area that Earth receives, and during dust storms, available light can drop to near zero. Artificial LED lighting tuned to the wavelengths most efficient for photosynthesis, primarily red and blue, could supplement or replace natural sunlight. But the electrical power required to illuminate greenhouse facilities at agricultural scale would be substantial. Water, while theoretically available from subsurface ice, must be extracted, melted, purified of perchlorate and other contaminants, and continuously recycled through the hydroponic system with near-zero losses. Any leak, any contamination event, any equipment failure in the water recycling loop could cascade into a food production crisis within days. Alternative food production strategies under investigation include bioreactors using algae and cyanobacteria. These photosynthetic microorganisms can convert carbon dioxide and water into biomass that is rich in protein, carbohydrates, and lipids while simultaneously producing oxygen as a metabolic byproduct. Spirulina, a blue-green alga already consumed as a nutritional supplement on Earth, is one leading candidate. Bioreactors have the advantage of being more compact and faster growing than traditional crops, and they can operate in enclosed chambers without natural sunlight. However, a diet based entirely on algae paste would be psychologically devastating over the long term. Food variety, flavor, and the social ritual of shared meals are deeply important to human well-being. And any Mars colony that fails to provide a diverse and palatable food supply will face morale problems that could undermine mission success just as surely as a radiation breach. Energy is the master constraint that underlies every other challenge of Mars colonization. Without abundant, reliable energy, you cannot extract water from ice. You cannot electrolyze water into oxygen and hydrogen for breathing and fuel. You cannot heat habitats, you cannot power greenhouses, you cannot run life support systems. You cannot manufacture building materials, and you cannot communicate with Earth. Solar power on Mars is severely compromised by the planet's greater distance from the Sun, the thin but dust-laden atmosphere, and the ever-present threat of global dust storms. The solar irradiance at Mars orbit averages about 590 watts per square meter, compared to roughly 1,361 watts per square meter at Earth's orbital distance. After accounting for atmospheric attenuation, panel efficiency, and the day-night cycle, a solar installation on Mars would need roughly 2 to 3 times the panel area of an equivalent installation on Earth to produce the same daily energy output. And even then, a months-long dust storm could reduce output to near zero. Wind power is not a viable alternative because the atmospheric density on Mars is less than 1% of Earth's. Even at very high wind speeds, the dynamic pressure, the force the wind exerts on a turbine blade, is negligibly low. A wind turbine on Mars would produce almost no useful power. The most promising energy source for a Mars colony is nuclear fission. NASA's Kilopower project, which ran its key demonstration test, called Krusty, 4-kilowatt reactor using Stirling technology, in 2018, proved that a small, portable fission reactor using a solid uranium-235 core could generate 1 to 10 kilowatts of electrical power continuously for more than a decade without refueling. The system is compact enough to fit on a Mars lander and operates independently of sunlight, dust, or weather. A cluster of 4 10-kilowatt kilopower units could provide 40 kilowatts of steady electrical power, enough to support basic life support and science operations for a small crew. However, 40 kilowatts is a tiny amount of power in the context of sustaining a colony. For comparison, the average American home consumes about 1.2 kilowatts of electrical power continuously. A settlement of 1,000 people, even at drastically reduced per capita consumption, would require megawatts of baseload generation. This pushes the discussion toward larger small modular reactors in the 100 kilowatt to megawatt range, which are under development for terrestrial applications but have never been designed for, tested in, or launched to another planet. Beyond fission, nuclear fusion remains the ultimate energy prize. A fusion reactor operating on deuterium and helium-3 or on deuterium-tritium fuel cycles could theoretically provide virtually unlimited clean energy. But as of early 2025, no fusion reactor on Earth has achieved sustained net energy output. The ITER project in southern France, the world's largest fusion experiment, is not expected to achieve full deuterium-tritium plasma operations until the 2030s at the earliest, and practical commercial fusion power plants are generally estimated to be decades beyond that. Counting on fusion to power a Mars colony is, at this point, a faith-based proposition rather than an engineering plan. The interplay between energy, water, food, and oxygen must be understood as a single integrated system rather than a collection of independent problems. On Mars, electricity would be used to heat ice into liquid water, to electrolyze water into molecular oxygen for breathing and molecular hydrogen for fuel and chemical feedstocks, and to power the environmental control systems that maintain habitable temperature and pressure inside structures. Oxygen and carbon dioxide would cycle between human respiration and plant photosynthesis in the greenhouses. Wastewater from human hygiene, food preparation, and biological waste processing would be reclaimed through filtration and chemical treatment and recirculated into the hydroponic systems. Food waste and human waste would be processed in anaerobic digesters or composting systems to recover nutrients for agriculture and potentially generate methane for supplemental energy. Every gram of every substance would need to be tracked, recycled, and reused with fanatical efficiency. The International Space Station's environmental control and life support system already operates on these principles, recycling approximately 90% of the water aboard the station. But ISS crew members number only 3 to 6, resupply missions arrive every few months, and ground control in Houston is available 24 hours a day via near-instantaneous communication. On Mars, the colony would be on its own for the better part of 2 years between launch windows. Communication delays would prevent real-time troubleshooting, and any failure in the closed-loop life support system could become lethal within hours or days. The ISS water recycling system and oxygen generation system have experienced multiple failures, requiring spare parts and expertise from Earth. On Mars, the colony would need to manufacture its own spare parts, train its own technicians, and carry sufficient redundancy to survive any plausible combination of simultaneous failures. The psychological dimension of Mars colonization may be the single factor most likely to determine whether a mission succeeds or fails, and it is the factor that receives the least engineering attention. The human mind evolved in rich, complex social environments with dozens to hundreds of regular social contacts, varied sensory experiences, the freedom to move across open landscapes, the comfort of familiar weather patterns, and the knowledge that help was available in times of crisis. A Mars mission strips away virtually all of these psychological supports. A crew of 4 to 8 people would be confined together in a habitat roughly the volume of a modest American house for a minimum of 2 to 3 years, including transit time. They would have no physical contact with anyone outside their crew. Communication with family, friends, and mission support on Earth would be subject to a round-trip delay of 8 to 48 minutes, depending on the relative positions of the two planets, making real-time conversation impossible. There would be no fresh air, no open sky, no trees, no animals, no weather variation, no spontaneous encounters with strangers, no ability to simply walk away from a conflict and cool down. The landscape visible through any window or during any extravehicular activity would be the same unchanging red desert. Day after day, month after month, year after year. The Mars 500 experiment, conducted by Russia's Institute of Biomedical Problems between 2010 and 2011, provides the closest terrestrial analog to these conditions. 6 male volunteers were sealed inside a 550 cubic meter habitat complex in Moscow for 520 consecutive days, simulating the duration and communication delays of a Mars round-trip mission. The results were instructive and concerning. Over the course of the experiment, the crew's sleep-wake cycles drifted and fragmented. One crew member developed mild to moderate depressive symptoms that persisted for nearly the entire duration of the mission. Another suffered from chronic insomnia and severe fatigue. Interpersonal conflicts, though not catastrophic, increased over time. Researchers found that the 2 crew members with the highest stress levels were involved in 85% of all recorded interpersonal conflicts within the group. Activity levels declined as the months wore on. Crew members spent increasing amounts of time sedentary, even during waking hours, exhibiting what researchers described as behavioral hibernation, a pattern of energy conservation that comes at the cost of productivity, social engagement, and psychological well-being. NASA's CHAPEA, Crew Health and Performance Exploration Analog, program has been building on these lessons. The first CHAPEA mission placed 4 volunteers inside a 1,700 square foot 3D printed habitat at Johnson Space Center in Houston for 378 days, from June 2023 to July 2024. The crew simulated Mars surface operations including crop cultivation, simulated spacewalks, resource limitations, equipment failures, and communication delays of up to 22 minutes each way. The results confirmed that consistent physical exercise, a balanced and varied diet, meaningful work, and mutual social support among crew members were essential for maintaining mental and physical health over long durations. The study also highlighted the importance of crew autonomy, because communication delays prevented real-time guidance from mission control. The crew had to develop their own decision-making protocols and conflict resolution strategies. This requirement for autonomy is a double-edged sword. It empowers crews and builds resilience. But it also means that if a crew's interpersonal dynamics break down, there is no external authority that can intervene quickly enough to prevent escalation. The Hawaii Space Exploration Analog and Simulation, known as HICs, conducted multiple long-duration isolation studies in a dome habitat on the slopes of Mauna Loa volcano between 2013 and 2017. These studies, involving crews of 6 living on simulated Mars rations with communication delays and limited resources, consistently identified team composition, social support structures, and individual psychological resilience as the primary determinants of mission success. Personality clashes that would be trivial in normal life became magnified under confinement. A disagreement over dishwashing schedules or personal space boundaries could escalate into a simmering resentment that poisoned the social atmosphere for weeks. The lessons from HICs, Mars 500, and CHAPEA converge on a single conclusion. The psychological environment inside a Mars habitat is not a secondary concern to be addressed after the engineering problems are solved. It is a core engineering problem in its own right, as critical to mission success as radiation shielding or oxygen generation. Future Mars missions will need to incorporate AI-powered psychological monitoring systems that track crew members' vocal patterns, facial expressions, sleep quality, and social interaction frequencies to detect early warning signs of depression, anxiety, or interpersonal conflict. Virtual reality systems that simulate Earth environments, forests, beaches, bustling city streets, could provide sensory relief and combat the monotony of the Martian landscape. Private communication channels with professional psychologists on Earth, despite the time delay, could offer a pressure valve for emotional distress. But ultimately, the crews selected for Mars missions will need to be among the most psychologically resilient humans ever assembled. Individuals capable of maintaining composure, empathy, and productivity under conditions of isolation and stress that no human being has ever endured in all of history. The dream of terraforming Mars, of transforming the entire planet into a second Earth with breathable air, liquid oceans, and green landscapes, is perhaps the most seductive and the most misleading idea in the entire Mars colonization discussion. The concept is simple in principle. Release enough greenhouse gases into the Martian atmosphere to warm the planet. Melt the polar ice caps, thicken the atmosphere to breathable levels. Introduce photosynthetic organisms to generate oxygen and wait. Over time, the logic goes, Mars would gradually become habitable without pressure suits or sealed habitats. Science fiction has painted this vision in vivid colors, and it has captured the public imagination. But the scientific reality, as assessed by NASA and independent researchers, is devastatingly clear. Terraforming Mars is not possible with any technology that currently exists or is foreseeable in the coming centuries. A landmark NASA-supported study published in 2018 by Bruce Jakosky and Christopher Edwards in the journal Nature Astronomy systematically evaluated every proposed source of carbon dioxide that could theoretically be released into the Martian atmosphere. They examined the polar ice caps, which contain the largest known reservoirs of frozen CO2, and calculated that vaporizing all of the CO2 ice at the South Pole would increase atmospheric pressure by only about a factor of 2, from 600 pascals to roughly 1200 pascals. This is still barely over 1% of Earth's atmospheric pressure and far below the level needed to sustain liquid water or provide meaningful greenhouse warming. They then considered CO2 absorbed in the Martian regolith, which could potentially be released by heating the soil. Even with the most optimistic estimates, this source could add at most another 4% of Earth's atmospheric pressure. CO2 locked in deeper carbonate mineral deposits could theoretically contribute more, but extracting it would require heating the minerals to hundreds of degrees Celsius across vast areas of the planet, an energy expenditure that is, for all practical purposes, infinite. When all sources are combined, the total accessible CO2 on Mars falls far short of the amount needed to create an atmosphere thick enough to support liquid water or human respiration. The researchers concluded unambiguously that terraforming Mars cannot be done with currently available technology, even if sufficient CO2 could somehow be produced or imported. The absence of a global magnetic field means that any thickened atmosphere would be gradually stripped away by the solar wind, just as Mars's original atmosphere was stripped away billions of years ago. Data from NASA's MAVEN, Mars Atmosphere and Volatile Evolution, orbiter, which has been studying Mars's upper atmosphere since 2014, confirmed that the solar wind is actively eroding the Martian atmosphere today, carrying away roughly 100 grams of atmospheric gas per second. Over geological timescales, this rate is devastating. Even if humans could artificially inflate the Martian atmosphere, the solar wind would begin tearing it apart as fast as or faster than it could be replenished, unless the magnetic field problem is also solved. The most ambitious proposal for addressing the magnetic field deficit involves placing a massive electromagnetic shield at the Sun-Mars L1 Lagrange point, the location in space between the Sun and Mars where the gravitational pulls of the two bodies balance out, allowing an object to maintain a relatively stable position. The idea, first presented at a NASA Planetary Science Vision 2050 workshop in 2017 by Jim Green, then NASA's Director of Planetary Science, was that a sufficiently powerful magnetic dipole at L1 could deflect the solar wind around Mars, allowing the atmosphere to accumulate naturally. The concept is physically sound in principle, but the engineering requirements are staggering. The magnetic field strength needed to deflect the solar wind at L1 would require superconducting coils carrying enormous currents, sustained indefinitely by a power source that does not yet exist. The mass of such a structure, including power generation and cooling systems, would likely exceed anything humanity has ever launched into space by orders of magnitude. And even if it could be built and deployed, the timescale for atmospheric recovery would be measured in thousands to millions of years, not human lifetimes. Other proposed terraforming methods are equally impractical upon close examination. Elon Musk's suggestion to detonate nuclear weapons over the Martian polar caps would indeed vaporize some ice and inject CO2 and water vapor into the atmosphere. But analysis shows that the warming effect would be temporary. lasting only a few years before the released gases refroze, and the detonations would contaminate the surface with radioactive fallout, making the planet less habitable rather than more. The proposal to manufacture super greenhouse gases like perfluorocarbons on Mars requires access to fluorine-containing minerals, industrial-scale chemical processing facilities, and continuous production to replace gases destroyed by ultraviolet photolysis, an infrastructure that is decades beyond our current capability to deploy on another planet. A 2024 study proposed using engineered nanorods made from Martian minerals to trap thermal radiation more efficiently than greenhouse gases, claiming over 5,000 times the warming effect per unit mass. While theoretically interesting, the study acknowledged that manufacturing and dispersing the required quantity of nanorods across an entire planet remains a profound engineering challenge. The honest summary of the terraforming discussion is this: every proposed method either requires resources that do not exist on Mars in sufficient quantities, energy inputs that exceed humanity's total current production capacity, timescales that dwarf the span of human civilization, or some combination of all three. Terraforming is not a plan. It is an aspiration, and a very distant one. The realistic path to human habitation on Mars, if it happens at all, does not involve transforming the planet. It involves building small, self-contained habitats that bring Earth's environment with them in miniature. Pressurized domes or buried modules would maintain Earth-like atmosphere, temperature, and pressure inside while the lethal Martian environment rages outside. This is not colonization in the traditional sense of the word, where settlers spread across an open landscape and live off the land. It is more analogous to living in a submarine or a space station, permanently enclosed in an artificial bubble of survivability, utterly dependent on technology for every breath, every sip of water, every calorie of food. The romantic image of pioneers striding across an open frontier dissolves into a more claustrophobic reality of people living in tunnels and domes, surrounded by machines that must never be allowed to fail. Given all of these obstacles, the question that naturally arises is, why bother? If Mars is so hostile, so expensive, so dangerous, and so far from anything resembling a comfortable human existence, why does anyone seriously propose going there? The answer is multifaceted and speaks to some of the deepest currents in human psychology, philosophy, and strategic thinking. The first and most frequently cited rationale is species insurance. Earth, for all its hospitality, is not invulnerable. Asteroid impacts, supervolcanic eruptions, pandemic pathogens, nuclear conflict, runaway climate change, and other existential risks could, in the worst case, render Earth uninhabitable or drastically reduce the human population. A self-sustaining colony on Mars, even a small one, would ensure that the total extinction of humanity becomes virtually impossible. This argument was popularized most forcefully by Elon Musk, but it has roots in scientific thinking stretching back decades. A 2025 assessment published in planetary science literature identified Mars as the most promising candidate for an independent human settlement beyond Earth. Not because it is easy, but because every other option, Venus, the Moon, the outer solar system moons, is either more hostile or more resource poor. The species insurance argument is not without critics. Some ethicists and scientists argue that the resources required to establish a Mars colony would be better spent mitigating existential risks on Earth, and that presenting Mars as a backup plan may reduce the political urgency to address climate change, nuclear proliferation, and other threats to Earth's habitability. This is a legitimate concern, and it deserves serious engagement rather than dismissal. The second rationale is the technological and scientific spillover effect. The history of ambitious exploration programs demonstrates repeatedly that the technologies developed to meet extreme challenges find unexpected applications in everyday life. The Apollo program of the 1960s and 1970s accelerated the development of integrated circuits, fly-by-wire avionics, water purification systems, freeze-dried food, fireproof materials, and medical telemetry, among dozens of other innovations. A Mars colonization program would drive advances in closed-loop life support, radiation protection, telemedicine, autonomous robotics, materials science, energy generation and storage, water recycling, and precision agriculture. These technologies would directly benefit Earth. The radiation shielding developed for Mars habitats could protect workers in nuclear facilities or patients undergoing radiation therapy. The closed-loop agricultural systems designed to feed Mars colonists could revolutionize food production in arid regions, urban environments, and disaster zones on Earth. The energy-efficient environmental control systems needed for Mars would reduce the carbon footprint of buildings and industrial processes here at home. The relationship between Mars colonization and Earth sustainability is not zero-sum. Investment in one can accelerate progress in the other. The third rationale is the value of international cooperation. A Mars mission is too large, too expensive, and too complex for any single nation or corporation to undertake alone. Estimates for the total cost of establishing a minimal self-sustaining Mars colony range from $100 billion to several $trillion, depending on scope and timeline. This scale of investment demands the participation of multiple spacefaring nations, pooling resources, expertise, and political will. The International Space Station, despite its flaws and political complications, demonstrated that nations with deep geopolitical tensions can collaborate productively in pursuit of a shared scientific goal. A Mars program could extend this model, creating new frameworks for international cooperation that transcend the rivalries and zero-sum thinking that dominate terrestrial politics. The process of negotiating who contributes what, who has access to what resources, and how decisions are made collectively could establish precedents for addressing other global challenges, from climate change to pandemic preparedness. The fourth rationale is perhaps the hardest to quantify, but the most deeply human: the drive to explore. For at least 100,000 years, Homo sapiens has been expanding into new environments. Our ancestors walked out of Africa and spread across every continent except Antarctica. They crossed oceans in wooden boats, climbed the highest mountains, descended to the deepest ocean trenches, and eventually left Earth's surface altogether. This pattern of exploration is not merely about resource acquisition or survival optimization. It is woven into the cultural and possibly biological fabric of our species. The impulse to see what lies beyond the next hill, to push beyond the known boundaries of the world, has driven artistic creation, scientific discovery, and philosophical inquiry throughout human history. Mars represents the next horizon. The first human footprint in Martian dust would be a moment comparable to the first human footprint on the shores of a new continent tens of thousands of years ago. Not just a step for the individual, but a declaration that the human story is not finished, that we have not yet reached the limits of what we can dare and achieve. The educational and inspirational value of a Mars program should not be underestimated. The Apollo missions ignited a generation's interest in science, technology, engineering, and mathematics. Enrollment in engineering programs surged during the space race. Young people who watched Neil Armstrong step onto the lunar surface grew up to become the scientists and engineers who built the internet, decoded the human genome, and developed the smartphones that now connect billions of people. A sustained Mars program would have a comparable cultural effect. Children who watched the first crew land on Mars would grow up understanding that the most daunting challenges yield to sustained effort, creativity, and collaboration. That is not a trivial outcome. In a world increasingly plagued by cynicism, political fragmentation, and a sense of diminishing horizons, the spectacle of humans setting foot on another planet could serve as a powerful counter-narrative. A reminder that humanity is capable of extraordinary things when it chooses to work together toward a shared goal. But we must be unflinchingly honest about what Mars colonization is not. It is not an escape hatch. It is not a lifeboat for 8 billion people fleeing a damaged Earth. Even the most optimistic projections envision transporting only thousands, perhaps tens of thousands, of people to Mars over the course of decades. The vast majority of humanity will live and die on Earth regardless of what happens on Mars. The notion that Mars colonization absolves us of the responsibility to address climate change, biodiversity loss, ocean acidification, and resource depletion on Earth is not just wrong. It is dangerous. As Katherine Hayhoe, a climate scientist at Texas Tech University, has warned, Mars is not an escape hatch for Earth. If we do not reduce greenhouse gas emissions, human civilization on Earth will be overwhelmed by climate change long before Mars is ready to host any significant number of people. Andy Weir, the author of The Martian, put it even more bluntly: no matter what problems Earth has, it is far easier to fix Earth than to colonize Mars. He is right. Even in its most degraded state, Earth possesses a thick atmosphere, a global magnetic field, abundant liquid water, fertile soil, a complex biosphere, and a gravitational field perfectly suited to human physiology. Mars has none of these things. Repairing Earth's damaged ecosystems, transitioning to renewable energy, reducing emissions, protecting biodiversity, and building resilient societies is orders of magnitude easier and cheaper than building a civilization from scratch on a barren, irradiated desert world 140 million miles away. The proper way to frame the Mars question is not, should we go to Mars instead of fixing Earth, but rather, can we pursue both simultaneously? And can each effort strengthen the other? The answer, based on the evidence, is yes. But only if we maintain intellectual honesty about the limitations of Mars colonization and resist the temptation to use it as a psychological escape from our terrestrial responsibilities. The technologies developed for Mars, life support recycling, energy efficiency, closed-loop agriculture, radiation protection, telemedicine, AI-assisted decision-making, will flow back to Earth and help address the very problems that make some people want to leave. The perspective gained from attempting to build a livable environment on a dead planet will deepen our appreciation for the living planet we already have. The international cooperation required for a Mars program will build institutional frameworks for addressing global challenges, and the sheer audacity of the endeavor will inspire a generation to believe that hard problems are solvable. But none of this works if Mars becomes an excuse, a rhetorical device that allows politicians, corporations, and individuals to shrug off Earth's problems because we can always go to Mars. We cannot always go to Mars. Most of us cannot go to Mars at all. And the Mars that we could go to is not a lush paradise waiting to be settled. It is a frozen, poisoned, irradiated wasteland that will fight every human attempt to survive on its surface with the full, indifferent force of physics, the food, water, air, gravity, magnetic shielding, and social richness that you enjoy right now. Reading these words, breathing without a mask, drinking clean water from a tap, stepping outside into weather that will not kill you, are the products of 4.5 billion years of planetary evolution and 3.8 billion years of biological evolution. They are not guaranteed. They are not permanent. They are not replaceable at any price. If we possess the ingenuity and determination to build habitats on Mars, to cross 140 million miles of void and survive on a world that offers nothing but dust and radiation, then we surely possess the ingenuity and determination to protect the extraordinary, irreplaceable, life-sustaining systems of the planet that made us. The challenge of Mars is, in the end, a mirror. It reflects back to us the true value of Earth. It shows us what it would cost to build from scratch what we already have for free. And it asks us the hardest question: if you had to recreate everything that keeps you alive, would you finally understand how precious it all is? Mars does not need us. Earth does. And perhaps the greatest gift of the Mars dream is not the colony we might one day build on another world, but the clarity it gives us about the world we must never stop fighting to save.